Welcome to this Magdalen webinar. I'm David Clowry, President of Magdalen College, and we're delighted that there's over 100 people listening in today of all ages and from many countries. And today we're going to hear about the very exciting topic of magnetism. Everybody is interested in magnetism, and they always have been. Magnetism is very useful, but it's not magic. It's something that can be understood with science, and scientists have been researching on magnetism to the present day. And this is especially true with our speaker today, Dr. Alexy Karenowska. Alexy is a fellow by special election at Magdalen College and conducts her research on magnetism in the Department of Physics in the university. She is also the Director of Technology at the Institute for Digital Archaeology, which documents, preserves, and recreates the world's heritage. Alexy started as an undergraduate in engineering, studying engineering at Magdalen, and graduated in 2007. She then did research for a DPhil in physics and was elected a fellow by examination. And Alexy is our widening participation fellow and has a special interest in helping school students and potential student applicants and their teachers learn more about Magdalen College. She also works to bring to life the important relationships between the sciences, the arts, and the humanities. And we're delighted that Alexy will be speaking today on the magic of magnetism, intrigue and adventure from antiquity to the modern day. And I encourage you to type questions in the Q&A facility on Zoom, and Alexy will answer them at the end of her talk. So over to you, Alexy.
Thank you so much for that very kind introduction, and welcome everybody. It's wonderful to be able to join you today, albeit virtually. Now I'm going to start right now by just sharing some slides with you. Here we go. Okay. So, as the President has explained, I'm going to be talking to you today about magnets and magnetism. Now, magnetism is something that is at the same time sort of completely everyday and really intriguing. So we learn about it at school, and you've probably seen pictures, something like this, that show the lines of magnetic field that a bar magnet like this produces, and they start at its north pole and they end at its south pole. And you've probably also learned that the like poles of magnets repel and the unlike poles attract. So if you put two norths together like this, they don't want to know each other, they put each other away, and two souths are the same. Okay, but if you pair up the opposites, they stick together. And people have been aware of magnetism as a phenomenon for thousands of years. Naturally occurring magnets in the form of a mineral called magnetite, there's a picture of it on the slide there, can actually be found just lying on the ground in many parts of the world. And you can see those beautiful 8-sided crystals. It's a really intriguing kind of material. But although we can find these magnetic stones easily, it's impossible to understand just from looking at a magnet what magnetism is and where it really comes from. I could sit and stare at this magnet for an awfully long time and I wouldn't be any further on. And that's why the story of magnets and magnetism is arguably one of the most interesting in the history of science. Magnetism has long been connected with magic and mysticism. And even the word magnet has an origin that reflects people's perception of the mysteriousness of the effect. Now, in fact, there are two competing stories to explain how magnets got their name at the time of the ancient Greeks, so about 2,000 years ago. And one is that it's connected to the Magnetes tribe in the ancient region of Magnesia. And there's a picture of it there, a map of ancient Greece. And Magnesia was an area that was connected to all sorts of interesting myths and legends. So that's one story. The other story is that it's named after a shepherd called Magnes. And the story goes that Magnes was walking with his flock, with his sheep, on a mountain called Ida, Mount Ida in Greece. And all of a sudden, the iron nails that were in his boots and the iron end on his staff stuck to the mountain. They'd been attracted by the magnetic field, and he discovered magnetism. So I'll leave you to decide which story you would like to believe. They both seem to me to be equally good. And maybe it's the case that the sort of fascination that we feel about magnetism is to some extent a bit independent of how thoroughly we understand it. So I'm sure many scientists would agree with me by saying that even though I know quite a lot about magnetism and where it comes from, it still seems a little bit magic. It still seems incredible that it happens, even though I know, as the president said, that it's not actually magic. It can be explained by everyday science. And it really did take a long time for the principles of magnetic science as we know it today to emerge. And there's a famous American satirist, a chap called Ambrose Bierce, who, writing at the beginning of the 20th century, made a comment I made very much about this, about the long period of time that it took us to get to grips with magnetism. And this was in his Devil's Dictionary, which is a really fun book. So he gives two definitions in his dictionary. Firstly, he describes a magnet as something that's acted upon by magnetism. And then he goes on to define magnetism as something acting upon a magnet. Okay? And he makes the comment, the two definitions immediately foregoing are condensed from the works of 1,000 eminent scientists who have illuminated the subject with a great white light, etc., to the inexpressible advancement of human knowledge. Now, Bierce here is being a little bit unkind. By the time his dictionary was published in 1906, we'd actually made quite a lot of progress, but still, I think he made a point. Magnetism is extremely mysterious. Now, Ambrose Bierce was also himself a little bit of a mysterious person. So he was a Civil War soldier, a successful satirist, a journalist, and he disappeared. So he went off to take a closer look at the Mexican Revolution in 1914 and was never seen or heard of again. Now, another interesting Bierce fact, which has absolutely nothing to do with magnets or magnetism, but is fun anyway, is that he was one of 13 children, all of whom were given names beginning with the letter A. Now, it's not clear whether this was a sort of a point of principle or a point of practicality, but either way, they clearly saved a small fortune on school name tags and an awful lot of time with the quick unpick swapping them over. So there are lots of old wives' tales and superstitions that go alongside this sort of satire around magnetism, and many of these started centuries before Bierce. So they started in the classical period and they lasted many hundreds of years. So it was thought for a long time, it was said for a long time, that garlic, diamonds and onions, for example, stopped magnets from working. Presumably the people that made that claim had never tried, but who knows? I have to confess, I've actually never tried either, so maybe I'm being rather unkind here. But I think it is highly unlikely that an onion or a clove of garlic, or indeed a diamond, will stop your magnet from being magnetic. Now, there was also a school of thought that existed for a very long time that magnetism had its origin, and it occurred because of the stars. And in particular, the constellation we call Ursa Minor, the little bear, the one that looks a little bit like a pan with a handle. And this is a Hubble Space Telescope image of that constellation. And there's sort of an interesting deeper connection with between magnetism and navigation. So you might have used a compass, or at least seen one, and the needle inside is magnetic. It's probably the earliest piece of magnetic technology. And the idea is that it points in the direction of the Earth's magnetic North Pole. Now, before compasses, the only way that people could navigate at sea in the dark at night was to use the stars. And in the Western world, the magnetic compass, which was invented in the 13th century, completely revolutionized people's ability to travel. And generally speaking, it was a book that was published in 1269 by a chap called Peter Peregrinus, which is considered to be the first Western description of the use of a compass for navigation. So people, as they say, started to use compasses at least as early as the 13th century. But actually, they then went on to use them for nearly 400 years before they actually worked out how they worked. And in the end, it was an English doctor, a man called William Gilbert, who finally worked out and popularized as well the understanding that the reason that a compass worked was that the Earth itself is magnetic. The Earth has a core of molten iron. It's like a giant magnet. And remarkably, the way that Gilbert did this, he did it in the year 1600, or he published an important book on this topic in 1600. The way he did it was to do a series of experiments, and the results of these experiments convinced the world of his theory. And this doesn't seem very revolutionary now, because that's what we do as scientists, but that idea of the experimental scientific method was very new at that time. So what Gilbert did was that he made little round miniature Earths out of magnetic material. And he showed, there's a picture of one on the slide there, and he showed that little pieces of iron wire would make a pattern just like that sort of mapped the behavior of a compass as you move around the globe. So the way that the iron wire, the angle that the iron wire made around the outside of his little miniature Earth was just like the angle that a compass needle makes as you move around the globe, maybe in a ship. Now, Gilbert was another interesting character. The history of magnetism is full of these amazing characters. He was born in Colchester, and he actually was a medic. He got a medical degree from John's College, Cambridge. But despite that, he did okay. And he became the personal medic to Elizabeth I from 1601 to 1603. And then actually James I took him on when he took the throne. But we believe that Gilbert died of the plague in 1603. It's not really that clear how a doctor, a very successful medical person, sort of got into magnetism. But then I have to say that experience has taught me that this is true of many of us magneticians. Magnetism finds us. Now, in the last 150 years, magnetism has not only become much better understood, but it's made its way into our lives through a whole range of remarkable technologies. Magnetic resonance imaging, for example, is a technique that's used in hospitals, and it allows us to use magnetism to get extremely high resolution images of our insides. And the image actually on the left-hand side of the slide there is the inside of my head. I was extremely relieved to find that there is a brain inside there. And some people had placed bets and were quite disappointed. But this is an absolutely remarkable technology, and is something that has really changed and made a step change in our ability to diagnose people's conditions and also operate effectively. Now, new material science also allows us to produce very strong magnets. That's what the little cubes are there on the right-hand side of the slide. And also to do really interesting levitation experiments like the one you see on the top of the slide there. Now that's an image that looks a little bit like something from outer space, right? Like a sort of a cloud on the surface of some sort of distant planet. But actually it's taken not in outer space, but in my lab. And it's a magnetic sphere that's hovering above a piece of a special class of material called a superconductor. And it's in a pool of a liquid that's 100 degrees cooler than Antarctica, a very, very cold liquid. And also, so a bit more practically than that, magnetism plays a crucial role in computing. So information is written and read onto the hard disk of a computer magnetically. Now, there are also, as well as these these technological applications of magnetism in devices and complex systems, there are also, of course, lots of uses that we put magnets to in our homes, whether it's sticking notes to our fridges or keeping our cat flaps closed. There are lots and lots of things that we do with magnets in the house. And a fun use we can put them to is also some magnetic detective work. And this is where, if you've brought some, your loose change and your magnet come in. Now, what I'm going to do is I'm going to stop the screen share here and have a look at, here we go, just bear with me a moment, have a look at some of these items here. So if I just move the camera down, I brought my own supply here of loose change. Make sure we've got that in the right position there. Now, here we go. So we're going to do some experiments here, and I'm also going to suggest some further experiments that you might want to do in your own time at home. So there are three metals that are magnetic: iron, nickel, and cobalt. Now, iron is a really common and inexpensive metal, and it's the main ingredient of steel. And when we encounter magnetic objects in our homes, it's generally because they contain iron or steel. Now, one way that you can check to see if coins are genuine is to see if their magnetic properties are as they should be. Now, some coins, as you will discover if you've got your magnet and your coins, are magnetic. They contain iron, and others aren't. Now, coins are often made out of more than one metal. So they might be copper-plated steel, for example, and you can't tell by looking at them. So a copper-plated coin looks exactly the same as it would if it was made out of pure copper. But you can sniff out the steel inside a copper-plated coin and discover whether it is indeed a copper-plated steel coin or a pure copper coin using a magnet. So what I've got here to start us off is a set of current UK coins. So first of all, let's have a look here and see which ones are magnetic. So if you have some too, you can also join in. So let's have a look. So the £2 coin, £1 coin, no. It's all a bit disappointing, no. Okay, oh yes, okay. So the 10p, the 5p, the 1p, and the 2p, yep, all nice and magnetic. So that's because, so in the case of the 1p and the 2p coins, are made from copper-plated steel. This outer coating of the copper color and the copper metal is just a thin layer. So here, though, is a little bit of a mystery. So over on the other side of the page here, I've got another example of these three coins. So I've got another 10p, another 5p, and another 1p. And these guys, unlike their friends, don't want to know about the magnet. They're not interested in the magnet at all in comparison to these ones. And that's because 1p and 2p coins have only been made from copper-plated steel, which is what these are, since 1992. And before that, they were made from a non-magnetic alloy of copper. And there are still plenty of these in circulation. So this is let's have a look here. This is a 1989 2-pence piece. Now, I have to confess that I couldn't find a 2-pence to match this. I went through all the kitchen drawers this morning and I couldn't find a pre-1992 2p. So that's a challenge for you. They are out there, I promise. So you should be able to find non-magnetic and magnetic versions of the 1 and 2p's. And the story is very similar for the 5p and the 10p coins. These went magnetic in 2012. So these are magnetic, these are non-magnetic. And there's some fun detective work that can be done with other currencies too. So let's see what we have here. Here, I've got a much stronger magnet, okay? It has to stay in this box because otherwise it's too easy for it to fly out and damage something. So I've got some other currencies. Let's just bring these on now. If you are watching from the United States, unfortunately, no US coins are magnetic. It's a little bit disappointing. An interesting fact, though, is that the notes, so American banknotes, are actually magnetic. So there is a pattern that's written in magnetic ink on the surface, and this is used for automated identification and detecting forgeries, but they will only stick to a really incredibly strong magnet. So you can't, even with my super strong magnet in the box, unfortunately, it's not possible to show you that magnetism, but I promise it's there. Okay, so what about other currencies? So Jordanian currency, really great if you want to have some fun with magnetism. So I'm going to take this 10 piastre coin here. There we go. You see how it sticks to that magnet. Oh, the 1p wants to join in as well. Okay, and I think I can probably even balance, yep, on top. I can get another 5 piastres there. And a further one. Will it let me do that? Yep, absolutely. And I think I can add to that. Here we go. So euros. The copper euro coins, so 1 cent, 5 cents, and I've got another 5 cents here, I think. These are all magnetic. The other coins aren't, unfortunately. So if you try a 1 euro coin, these are not magnetic at all, nor are the 50 cents and the 2 cents, but the 1, 2, and 5 cents are, and maybe I can get that to, oh dear, it all fall down. So this is a really fun sort of, I don't know what you would describe this as really. This is sort of the interface between science and art, right? You have to see whether you can build a nice structure. Let's see what else we have here. So if you happen to have any Russian currency, this is also nice and magnetic. So this is 10 rubles. These are really magnetic. So I can put 10 rubles there, maybe another 10. And there's a similar story with the 5 ruble coins here, as with our 5p's, 10p's, 2p's, 1p's. So older 5 ruble coins are non-magnetic. That's an example there. But the newer ones are magnetic. So I'll try and add that to my sculpture. There we go. So I'm going to get it to stand up. So there. I can recommend this as a fun activity. You learn something about the composition of the coin. So like I said, it's not that obvious what all of these coins are made out of. So you can't tell from the color what kind of metal is inside. So using a magnet is a really good way of identifying what coins you're looking at. And at the same time, you can learn a little bit about the history of how our currency has been produced and the different choices that have been made about the metals that have been involved. So I'm going to go back. So I'm going to move my sculpture to one side here and my very strong magnet. And let's go back now for a moment to the slides. And I'll show you a few more interesting magnetic facts. Here we go. So hopefully that's back for everybody. So, as I said, we've looked at these activities that you can try in your own home with your leftover currency. And also, we discussed a range of magnetic technologies. But there's also a whole range of really interesting magnetic effects that are invisible to us in our everyday lives, but that can be investigated in the laboratory. And one of these is something called a spin wave. Now, a spin wave is a kind of magnetic wave that can travel at high speed through a magnetic material. Now, it's hard to detect and you need special equipment, but it's basically just like a water wave. But rather than being defined by a moving variation in height of water, like a water wave, it's defined by a moving variation in strength of magnetic field. So exactly the same stuff, the same magnetic field that sticks your fridge magnets to the fridge. And the very first person to measure a spin wave was, of course, a Magdalen scientist. So James Griffiths was a long-time fellow of the college, and in fact, our 39th president from 1968 to 1979. And many old members watching today, even if they didn't have the opportunity to meet Griffiths in person, will probably be familiar with this portrait of him, which for a long time hung in the new rooms, if you know the space, where it oversaw many, many generations of schools' dinners. So I mentioned a moment ago that we can think about a spin wave just like a sort of magnetic version of a water wave. And it turns out that this comparison is not just useful for our understanding of what a spin wave is, it's also really helpful if we're interested in studying the more exotic aspects of the way that water waves behave. And I'll explain why. So the picture here shows something called the Severn bore. It's essentially a big wave that sweeps periodically down the River Severn, and it's caused by the tides. Now, it turns out that this is a very interesting effect. It's caused by what we describe as the non-linearity of the water. It's a really interesting phenomenon. And you can see that it involves a sort of big wave at the front that the surfers are riding, and then a train of smaller ones that follow it. The water is completely flat ahead of this wave at the front here. There's a big area of still water. Now, as I said, this is interesting, and people who are interested in the study of water and water waves really want to study these things. But if you want to do it in person, you obviously have to have a lot of patience, because it only happens every now and again. And if you miss it, you've missed it, right? You can't be late. And the weather's not always good. You need a stout pair of Wellingtons and probably a packed lunch, okay? So not that practical, exciting, but it has its frustrations. But it turns out that we can actually recreate the very same phenomenon, so the same kind of wave, in the lab using spin waves, using this interesting kind of magnetic wave. And I'm going to show you how we do that. So this is a photograph of a little piece of magnetic material highlighted there. So this is a little strip of a magnet. It's a kind of brown color. And then we also have, so that the arrow there is showing you where the wave is going to propagate. So the wave is going to propagate along this strip of magnetic material. It's a couple of millimeters wide. And what I'm going to show you now, so that's the experimental system that we start with. This is what we're going to measure. And now I'm going to show you data that we've collected from this little strip. Okay, so we can excite just the same kind of wave. Here we go. Okay, in this little piece of magnetic material. Now, we've cheated a little bit. This wave is propagating very, very fast in comparison to the wave in the river. Okay, so it's an effect that we have to slow down in order to see it. But you can see that this is an extremely powerful kind of ability to have, because we can recreate this propagating wave endlessly. You know, we can keep doing it. Oh, whoops, I'm sorry. The slides have gone crazy here. We can keep doing this as often as we like, and really get to grips with the dynamics of this phenomenon, the way that the water wave behaves. Now, my slides have started to misbehave a little bit. Let's see. Here we go. So, okay, so let me show you that again, because I think you were robbed of another. There we go. There it goes. Okay. So we can capture as well the same physics. So here we go. Yeah, can merge the two images. Okay, you have to use a little bit of imagination, but you get the idea. So we can capture the same physics, so these interesting phenomena that have to do with the propagation of magnetic waves in tiny little pieces of magnetic materials, together with an interesting set of behaviors that they show. So some interesting effects that are specific to these magnetic these magnetic waves, and we can use them to develop new kinds of information processing device, and we can potentially produce devices that have all sorts of advantages over today's state of the art. And this is exactly the kind of work that goes on in my laboratory. And these are some pictures of some little electronic devices that have been built exactly for this purpose. So these are magnetic circuits that are designed to produce, capture, and manipulate spin waves to perform information processing tasks. So we've covered a lot of ground, okay, from everything from shepherd's boots to new kinds of computing via loose change, a Magdalen scientist, and the River Severn. So I think it's time for me to stop now and to take your questions. Thanks so much for being so attentive. Okay. So I'm going to take a look here at the Q&A. So let's have a look. Oh, some great questions here. Okay, so from Andrew Rose. Thank you for your question, Andrew, here. So what's my favorite thing about magnets? Okay, that's a really great question. I think maybe my favorite thing about magnets is just the extent to which they always have a surprise in store for us. Like I mentioned before, they are, even, you know, when you know about their physics, when you know how they work, they're still just, the effect of magnets seems to be so magic and mysterious. And I think that I would never want to lose my sort of sense of wonder about how amazing it is that you have this invisible field that is able to have such a profound effect on pieces of metal and other objects. So yeah, it's a really good question. Okay. So we have another question here from Joanna Harrison. Joanna, thank you for your question. That's great. How the levitating sphere works. Okay, so this is a really good question. Let me see if I can share the screen with you again. Let's just move back. So what I'm going to do is I'm going to go back to the slide here and I can talk about that. There we go. Okay, so hopefully you can see that now. So the way this works is quite interesting. So what we have is, so I explained that this is a bath, a sea, a very, very cold liquid, okay? And it's actually liquid nitrogen. So we take the nitrogen in the air and we turn it into a liquid and it liquefies at very, very low temperature. So you can use it to cool things. And what's being cooled here is this little island that you probably spotted in the haze, okay? And this little island is made of a superconducting material. It's like at room temperature. So if you just held this in your hand while you were listening to me talk, this wouldn't seem very interesting at all. It just looks like a sort of, I wish I had a lump here, I'm afraid I don't. It looks like a sort of lump of, it's almost like coal, but it doesn't, but it's harder. It's like a black ceramic-like material. It's not magnetic, it's not very interesting. But if you cool it to very low temperature, something really exciting happens. So it becomes a superconductor, and a superconductor is a material that is able to pass electric currents through it. So it can let an electric current flow through it, but without any resistance at all. So you can, it doesn't heat up, it just allows that electric current to flow around it. And there's a sort of a subtlety, like a sort of a conspiracy, if you like, of the physics, that means that when it does that, when it turns superconducting, it tries to expel all of the any magnetic field that it has in it, okay? So the way that you get this to work, this is really, it's not easy to understand the detail of the physics of how this works exactly, but the way you get this to work is you take this piece of special material, the superconductor, balance the magnet on top with a gap in between. So I often use just a piece of cardboard or something underneath. And then when they're balanced, you cool this system down to below the temperature that this special piece of material goes superconducting. And when you do that, it gets frozen into position because of this process where the superconductor tries to get rid of the magnetic field that's going through it. And in fact, you get some of the magnetic field, the magnetic field from the sphere here, in combination with this interesting effect, sort of makes this assembly, the sphere and the island here, really, really solid. So as long as you keep this cool, you can push the sphere. You can, if you do it quickly, turn it upside down and put it back in again, and it will stay exactly in place. So it's a really interesting example of how the combination of magnetism and superconductivity can do really interesting things for you. Okay, so more great questions here. So Con and Agnes, how do you know whether a coin is attracted to the north or the south of magnets? Really good question. Now, it turns out that actually it will be attracted to both. So if you have, there's an important distinction here to be made between two things. One is a permanent magnet. So this is a permanent magnet, okay? It has a north and a south pole, and the direction of the magnetic field is defined by the way it's been. We use the term magnetized, okay? So what we've done is we've taken a piece of material that has potential to be a magnet, and we've actually applied a magnetic field to it to turn it into a permanent magnet, okay? And that's how you make a magnet. So this is a magnet, this is a permanent magnet. As long as we take care of it, it will always have a south pole here and a north pole here. That's different from something that's merely magnetic. So this coin here could become a magnet if I applied a really big magnetic field to it and I turned it into a magnet. But until that happens, it will just be attracted by the field from an already magnetized magnet. So that's slightly confusing, but I hope that makes sense. So in other words, there's a difference between something that we've already turned into a magnet and simply a piece of material that has yet to be turned into a magnet, but will feel the effect of a magnetic field. Okay. So somebody is also asking here, what makes a magnet stronger or weaker? Good question. So there are lots of things that can make a magnet stronger or weaker. One example, so the most boring example, is how strongly you magnetize it. So like I said, if you've got a material like iron that has the ability to be turned into a magnet, you can magnetize it weakly or strongly. So if you apply a really big magnetic field to it, you will maximize the magnetization and you will turn it into a very strong magnet. If, on the other hand, you apply a weak field, then you won't get quite so strong a magnet. That's a sort of boring answer. The more interesting answer is that it depends a lot on the material. Now, these magnets are quite weak. These are designed so that I can't harm myself with them, okay? So they won't, you can see that the coins aren't sort of leaping up from the desk to meet it. The magnet that's in my magic orange container here is treacherously strong, right? This is made out of a ceramic material called neodymium iron boron. So it looks like any other ceramic. So it's a sort of dark color, but it has a texture a little bit like porcelain. It's quite delicate. It has to be covered with a coating to make it nice and strong. But basically the engineering of really strong permanent magnets is all to do with the material science connected with the creation of materials that exhibit a really strong magnetic effect. And the chemistry of that is quite complex, but it's an extremely active area of research. Okay, so we've got some more questions here. Somebody is asking, are magnetism and gravity related? So I'd love to say that the answer was yes. Unfortunately not. So the only way that magnetism and gravity are related is that they're both fields. Okay, so the field is an important concept in physics. So the gravitational field that you can use to describe the effect of objects falling towards other massive objects, so an apple falling out of a tree, is really similar to it's a similar kind of idea to the one that we can use to describe the field that arises around the outside of a magnet. Okay, so what have we got? What is the purpose of the Earth being magnetic? Laura, okay, that's a great question, Laura. So I'm afraid that it's more of a philosophical, I can only give you a philosophical answer. Okay, so there's no real reason why the Earth has to be magnetic. But it's just a consequence of the fact that in the early days of the Earth's formation, heavy elements like iron were formed. So the other elements that we kind of take for granted on the surface of the Earth today are all a consequence really of the early lifetime of the planet, the kind of temperatures that it reached, etc. So it's very hard to say, you know, why that should happen exactly. But the consequences are enormous. So the Earth's magnetic field has a really important role in making sure that our atmosphere stays where it should be. And it's also obviously extremely useful to be able to use the Earth's magnetic field for the purposes of orienting ourselves on the surface. But in terms of explaining why it's actually magnetic, for a long time, so at the time of Gilbert, there was a lot of discussion actually about why it should be the case from a philosophical and also a religious point of view that the Earth should be magnetic. So I'm afraid I can't give you a scientific explanation, but you've touched on a really interesting philosophical question there. Okay, so we've got some even more questions here. What is Anwen? What is not known about magnetism? Okay, that's a great question. So much is not known about magnetism. As scientists, we always talk about, you know, the distinction between known unknowns and unknown unknowns, right? So there are certain things that we know that we don't know, and there are other things that we've yet to discover that we don't know. And magnetism is full of all sorts of subtleties like that. So there are plenty of mysteries connected with the origins of magnetism in certain materials. So some materials are magnetic, we don't quite understand why. The relationship between magnetism and superconductivity is a really important topic in this context. So superconductivity and magnetism have this interesting relationship where they fight each other to some extent, but you can use superconductors to produce big magnetic fields, and understanding the detailed physics of how magnetism and superconductivity interact is a really huge area of research. And then, of course, there are all sorts of interesting questions around these effects like spin waves that I've talked about, understanding how they work and how we can use them. Okay. We've had it. Why are some magnets stronger than others? I think I've already talked about that. I think in the context of the materials and how we use them. Okay. So Ned, what's the strongest magnet? Good question. I'm not sure I know the answer to that. So the very strongest magnets are actually produced using electricity. So you can go so far using, making like a lump of magnetic material. You can produce a really big magnetic field, and big enough, to sort of attract large magnetic objects. But if you want to produce really big magnetic fields, the kinds of fields that you need, for example, to do the magnetic resonance imaging of somebody's body, then you actually produce them using electrical currents. So an electrical current produces a magnetic field, and that was an effect that was discovered by a Danish physicist called Ørsted in 1820. And what Ørsted did was he took a piece of wire, and he was actually doing, this was an accidental discovery, as many great things are in physics. Took a piece of wire and he put he put an electric current down the wire. And he saw that a compass he happened to have nearby deflected, it moved slightly. And that was a really important moment in the history of magnetic physics. He really, from that observation, he was able to establish that electric currents produce magnetic fields. From that was really the birth of what we now call an electromagnet. So the biggest electromagnets will produce fields of 30 Tesla. So a Tesla is the unit of magnetic field. It's named after Nikola Tesla, you might have heard of. And 30 Tesla is about, put this into perspective, so this magnet probably produces a field of about 1/5 of a Tesla. So that is, and you can see how strong it is, okay? That is, it's still a lot of magnetic field, okay? So, so we're talking, so 30 Tesla is a really tremendously strong magnetic field. But these really strong fields tend only to be able to be produced for relatively short periods of time. So the strongest magnetic fields are what we call pulsed fields, and we use them to do experiments. So we can switch the magnetic field off and on for short periods, but we can't run it continuously because it wears out the equipment in different ways. So I would say between, there are probably pulsed fields of about 100 Tesla. There's a really, 30 Tesla certainly exist. I think 100 Tesla probably does as well. So really, really strong fields. Okay, so what else have we got here? So Roger Michael, magnets have an amazing history, but what's the future for magnets? I mean, I think that's another really interesting question. So we've got this extremely interesting series of events along the way of trying to understand magnetism. Actually, all sorts of really important discoveries have been made that have had a major impact on other areas of physics, especially the understanding of electricity and electromagnetism. So things like light, radio waves, microwaves, that kind of thing. I think that in the future, it's becoming increasingly clear that magnetic information technology, so new kinds of magnetic devices that will change the way our computers work, are going to become important. And I think that also the use of strong magnetic fields in an industrial context. So we're only just learning how to effectively control and and manipulate really, really strong magnetic fields. And these can be extremely useful for producing machinery that doesn't involve mechanical, where you can do work without mechanical contact between components. So levitation is one example. People might have heard of levitating trains, that kind of thing. That's an example of how the development of that technology certainly is all about magnetism and could have a big, big impact on our future. Okay, so why did I become a magnetician? Somebody has asked. That's a really good question. So I hated magnetism when I was at school. So I, as the president explained, came to Magdalen to read for a degree in engineering science, and the engineering degree in Oxford, which I can thoroughly recommend to anyone who's interested in physics or in engineering and making things of any kind, is like a mixed course. So you do civil engineering, you do electrical engineering, you do chemical engineering, you do mechanical engineering. And I was enthusiastic about that, but I had this really strong idea that I wasn't quite sure what I wanted to do in engineering, but I was sure that I wanted to do some engineering. But the only thing I was really sure about was that I didn't want to have anything to do with electricity or magnets, which I thought was really odd and mysterious at school. I didn't really understand why they worked. I could kind of learn the formulas and do well in the exams, but I was deeply suspicious of magnets and electricity. And of course, what happened was when I came to Magdalen, I'd sort of thought that this wouldn't matter too much, that I could sort of maybe just kind of get by on the part of the course that involved electricity and magnetism. And not really, not worry too much about it. But I discovered quite quickly, like in the first week that I arrived, that actually this was pretty serious stuff, that I was really going to have to either understand electricity and magnetism, or I wasn't going to last very long. And I was very, very lucky because I had a wonderful tutor who is still at Magdalen. He's the senior physics tutor at Magdalen, and John Gregg. And John, I confessed my distaste, the fact that I really didn't like electricity or magnetism, to John. And what he probably should have said is, look, just go away. But he didn't say that. He said, well, actually, if you look at it from a slightly different angle, what you'll realize is that actually this is something that's really, really profoundly interesting. And he persuaded me that I thought that I had the wrong kind of brain to understand electricity and magnetism. I thought of myself as being a kind of mechanically minded person who needed to be able to see things to understand them. But he encouraged me to embrace the fact that actually magnetism is mysterious, right? You can't expect to be able to look at it and understand what's going on. And that is why it's so wonderful. So, yeah, basically, I got into magnetism completely by accident. Would never have anticipated it at all, but it's been an amazing adventure. And the work that I'm able to do in the laboratory, and just in connection with the way that we study these systems, is now something that I find just enormously inspiring. So, some more questions here. How fast does a spin wave go? So a spin wave, the speed varies, good question. But typically at about 10,000 meters per second. Okay? So quite fast, but much slower than light. So light travels at 3 times 10 to the 8 meters per second, really, really fast, right? And spin waves travel at about 1/10,000th of the speed of light. So fast, but other phenomena in physics are faster. Okay, and Rachel here. What other things can you recreate in your lab with magnets that are like the River Severn one? Really good question. So we can also we can produce other kinds of wave effects. We like that you can also see on water, like waves that look a little bit like tsunamis. We can produce ripples. So in the effect when you drop a pebble in the water and all the waves come out, that's an effect we can recreate really easily. We can produce interference between waves. I'm not sure if you've seen that. So if you take 2 pebbles and you throw them close together, what you'll see is that the ripples from the 2 pebbles will add and subtract from one another, and you end up with an interesting wave pattern as a result of that. So anything you can imagine in water, right, you can reproduce in spin waves. Okay, could magnetism potentially be used, hang on, I've lost it, to make a time travel machine? I couldn't possibly say. No, I wish I had a hidden magnetic time machine in my living room, but I mean, it would be daft, silly to sort of say absolutely not. Of course, there are all sorts of, we have to ask really carefully about, what exactly do you mean by a time machine? That's a really interesting question in and of itself. It's not clear. There's no known way that you could use magnetism to make a time machine, but I am not going to say that you categorically can't use magnetism to make a time machine, because who knows, Okay, next question. Martha here, you are asking, are humans magnetic? If so, how are you all not stuck to the ground due to the Earth's magnetic field? Good question. So most things, so that there are actually different kinds of magnetism. So we use the term, we tend to describe, we call things magnetic when they're either magnets or they stick to magnets. Like this. Now, in reality, the science of magnetism is a little bit more subtle than that. And in fact, even things that are not magnetic, so, like my 20 pence coin, does actually respond to a magnetic field. And so do you. So people are mainly water, right? And water is what we call diamagnetic. Now, what that means is that when you apply a magnetic field to water, the water produces a really weak magnetic field that tries to fight the field that you apply to it. Now, what this means in practical terms, I will recommend that you Google levitating water drop or levitating frog. So if you take a really big magnet, a big superconducting magnet, and you put a drop of water in it, you will find something remarkable happen. So the water droplet levitates, just like the sphere that I showed you on the slide there. You can also do it with a frog, because like you, a frog is mainly water, but that seems a little bit mean. So the answer is that you do react to a magnetic field as a person, but you're not a magnet, okay? You can't be magnetized. And it's also important to recognize that the Earth's magnetic field is very, very weak. Now, there are certain animals that are able to use the Earth's magnetic field to orient themselves. There are bacteria and fish and birds, but humans, unfortunately, don't have that capacity. Otherwise, we would never have to carry a compass. Okay, so some more great questions here. So, Andrew Crowther, how does an MRI work when it's acting on human tissue that has little eye? Okay, so magnetic resonance imaging is an example of a technique that actually uses, it doesn't, the images that you see, those are not images of particles inside you. Magnetic resonance imaging actually exploits an interesting magnetic effect that has to do with the nuclei of atoms. Okay, so what you're actually looking at are the pieces of non-magnetic biological tissue inside you, and it's a very interesting effect. But yeah, it has to do not with the same kind of, this, not this kind of magnetism. It's a different effect that has to do with the nuclei of materials. Claire here. Why do magnets damage electronic devices? Well, basically because electronic devices also contain two things. One, currents, and if you have an electrical current flowing and you bring a big magnet next to it, it will deflect the current. It will affect the current, because the current itself is producing a magnetic field, and the two interact, they respond to each other, and your electronic device doesn't like that. The other thing is that there are magnetic components inside the machine. So it tends to do mechanical damage to all of the little gizmos inside when you bring a magnet up close. Sarah Dolan here, what do you think is the most interesting practical application of a magnet? That's a tough one, okay? There are so many interesting applications. I think that my answer has to be a slightly sneaky one. It's probably making a big magnet. So and studying magnetism. So one of the most interesting things that you could do with a magnet is try to understand how magnetism works. And so beyond all of these practical things, we can use magnetic fields to get at the physics of the nuts and bolts of how magnetism works. And that's something that I find really inspiring. Somebody who's also asked, can you make a magnet with items in the home? You can if you've got another magnet. So it's a little bit sort of chicken and egg, really. Literally, if you've got a chicken, you can make an egg. If you've got an egg, maybe you can make a chicken. If you have a magnet, you can make another magnet because you can magnetize things. If you've got even a weak magnet, you find that you can make a magnet out of, I'm looking for a pin or something, but I don't have one on the desk. If you stroke a pin on it, you will make the pin magnetic, but you do need to start with a magnet, unfortunately. Unless, of course, you happen to have a meteorite in your back garden. If that kind of falls into the garden, then those are often magnetic when they actually fall to Earth. So there's a lot of iron, meteoric iron is an interesting source of iron, and lots of iron in meteorites. They tend to be very magnetic. Okay, if the Earth's magnetic core is round, then why doesn't a compass get attracted to all of it, not just the North or South Pole? Good question. So that's because the magnetic field that the magnet, the compass needle, will follow the lines of the magnetic field. So if we go to see if I can just go back to the slide here to show you this. So here we go. It's fine. Here we go. So if I show you this picture again. Okay, so here, this is the magnetic field around a bar magnet, and this is really what the magnetic field around the Earth looks like too. It's just that it's sort of stretched out a little bit. You imagine making this sort of a round magnet rather than a long thin one. It's still got a North Pole at one end, a South Pole at the other end, and the magnets follow the compass needle will point in the direction of the North Pole in the case of a compass. So it's attracted, magnets, a magnet is always attracted to one or other pole of another magnet. So if you've got a South Pole, it will always be attracted. You can see with the same phenomenon here, the magnets aren't, they're not really sort of attracted to each other. They're attracted because of the shape of the field to the ends of each other. Yeah. And that's just a consequence of the way that the field works here. Okay. So Tabby here. Is it possible that there's a parallel universe without magnetism? That's a great question, Tabby. I mean, it's not impossible. Nothing is completely impossible. It's probably sort of a little bit unlikely because of the fundamental role. So it would have to be a universe that has very different physics from ours. So there are different kinds of parallel universe ideas. Some are more way out than others. Some people think that, you can have universes that have, totally different rules that govern the way that the physical world behaves. A slightly more conventional view of a parallel universe is that basically it has the same kind of physics as ours. It just happens to, either co-inhabit a space and not be visible to us, or exist in another dimension, kind of the same thing. So, if our physics kind of requires magnetism to exist, electricity and magnetism are a really fundamental thing. But again, it's a little bit like the time travel. I wouldn't be a scientist really if I said absolutely not. I think it's unlikely, but I can't prove that it's not possible. Another one from Sarah here. Do magnets maintain their strength underwater? Absolutely, yes. They're not affected by water at all. Someone else asking if you can make a magnet at home. As I said, what you need is a meteor. but other than that, you need a magnet to make a magnet. Why do the Earth's magnetic poles shift, and did the shifts have any effect on you or other scientists worked with magnetism? Really good question. They move because the iron that makes them up is molten, and obviously the Earth is spinning at really high speed and moving through space. So it's a dynamic system. This whole thing is kind of moving around. Fortunately, it's quite well behaved. Otherwise, so what I mean is that the Earth's magnetic core doesn't kind of spin around at high speed, because if it did, we would never have come into existence. Because like I said before, it's a really important part of the way that the ecology of the planet has evolved in the way that it has. But it does move. And in certain parts of the world, it actually moves by quite a lot. Okay, so it's like several feet a year in some cases, or several meters a year. It has an enormous effect on the way that, so there are people who study geomagnetism. They are geomagneticians, and that's what they do all the time. You may have heard that a pole reversal, so if periodically the direction of the Earth's magnetic field shifts, that's a pretty catastrophic event. So there's one group of people that think that this was responsible for the sort of mass extinction a very long time ago. It's really disruptive because of the effect it has on the climate and the atmosphere. But other than that, beyond, so fortunately, that doesn't happen too often, but people do try to predict when it's next going to happen. And one way to do that is to look at how the poles wobble. And we can look at the history of where the magnetic north has been because of the iron content in certain rocks. So there's a sort of, there's like a record that's kept in the geology of the Earth that enables people to understand how the poles have moved around. For my sort of research, which is mainly based in a laboratory looking at very sensitive devices, the only way that the Earth's magnetic field really affects us is that sometimes we want to get rid of it. And so in order to do that, we magnetically screen things. There are different ways that we can do that, and we try to back out the Earth's magnetic field. But in general, it's not too much of a problem. Okay, Rob here has asked, why are frogs magnetic? So frogs are magnetic because they're made mainly of water. So, and like I was saying before, this is not the same kind of magnetism as the magnetism that you get in a permanent magnet. It's something called diamagnetism. It's actually the case that most materials are weakly diamagnetic. What that means is that when you apply a magnetic field to them, they produce a magnetic field that is opposite to the field that you've just applied. They sort of fight the field. Water is quite diamagnetic, so that is, it produces quite a big magnetic field in the opposite direction to the one that you apply, and that's why the frogs levitate. I can recommend looking on YouTube for some of those videos, because the water, the blobs of water in particular, are very, very beautiful. You find yourself asking, it just seems so counterintuitive. It's really interesting. Okay, if spin waves can make waves in water, could they be used to disrupt water during natural disasters? Yeah, good question. So actually they can't. So that spin waves can't actually be used to make waves in water. They can just be used to sort of model. So they can model the waves in water, but in the magnetic material. So you can't sort of combine the two, but what you can do is you can produce like a copy of the water wave in the magnetic system. Certainly they can help you to understand how dangerous water waves propagate, but they can't actually sort of help you physically with these problems. Is a shame. Does magnetism alter chemical reactions? Another one from Rob. Yes, absolutely. In fact, Professor Clary, who is a chemist, I'm sure knows an awful lot more than I do about that particular topic. Absolutely, magnetism is very important in a whole range of chemical reactions. Someone is asking, what different experiments have I done in the lab? That's from Alex. Yeah, really good question, Alex. So we do a mixture of experiments in the lab. Some of them have to do with building new kinds of device. Others have to do with exploring how magnetism works. So I've done experiments where we look at making devices that are for storing information, for example. So like the chips that you get in your computer, but using magnetism. I've also done experiments that involve exploring these wave effects that we've described. So one of the experiments that has been quite interesting from this point of view is actually working out how you can do an operation that's called time reversal. Now, somebody mentioned time travel. Unfortunately, this had nothing to do with time travel, but there is a really interesting physical process by which basically you can take a wave. So imagine I've got a waveform like this, and you can, it's imagined that your wave is propagating in this direction. You can do an operation on it and you can cause it to reverse direction, which sounds really simple, but actually using just one piece of physics to do that is actually quite interesting and not so trivial. And that can be used in a whole range of information processing kind of applications. Then we have another question here. Does the anomalous magnetic moment of the muon still threaten the standard model? Oh, so that's a deep question. I think that's hard to answer in a very short sentence. There is still a lot of discussion about this particular topic, but I think that it's fair to say that over the last few years, a lot of progress has been made about understanding muon dynamics. And James, finally, what are the potential uses of spin waves for information processing? So this is a nice question to finish on. So one of the interesting things about these spin waves is that they are able, they allow you to use these sorts of wave effects. So just like the wave that we saw on the River Severn, and interference that I've described, and the kind of ripples that you can make on the surface of water, you can recreate those effects, but in really, really small pieces of magnetic material. So pieces of material that are a tiny fraction of a millimeter in size. And there's no other piece of physics that really allows you to do that. So you can use electromagnetism, you can try to do that, but at the sorts of frequencies that we do information processing. So information processing happens in what we call the microwave frequency range. So that's actually the same frequency range that your microwave oven works, and a whole range of other devices. But at those sorts of frequencies, electromagnetic waves have wavelengths that are too long to allow you to exploit those sorts of phenomena, these wave phenomena. Your computer would have to be, the size of this room if it was built on the basis of electromagnetic technology and use these effects. So essentially, one of the interesting things that we can do is sort of hybridize wave computing and digital computing. And in particular, there's some really interesting potential for doing that in the context of quantum information processing, which is something that we work on very actively in the lab. So the whole world of quantum computing, so going beyond the classical world of computing that currently is the baseline for our consumer devices, is a really important, or is going to be a really important development over the next decade, and something that magnetic physics has, I think, a lot to contribute to. So those were some really fantastic questions. Let's just make sure, is there anybody at this point that would like to ask a question but hasn't yet? So if anybody wants to raise a hand, I think we've gotten through a great range there of really good questions. So if there are no more, I'd like to thank you hugely for coming along this afternoon and for being such a great audience. As I say, that was a great range of questions. I hope you've enjoyed what we've talked about, and I hope very much to see you all again soon in person. So Magdalen is looking incredible, and we're all looking forward very much to being back there and able to host you once again. Thank you so much.